Hi everyone, and welcome to this Copernicus Marine Service training for ocean color. My name is Silvia Pardo. I'm an Earth observation scientist at the Plymouth Marine Laboratory in Plymouth, United Kingdom, and I'm here today to help you explore some of the ocean color products you can access through the Copernicus Marine Service. During this workshop, we will use Copernicus data to visualize maps and build time series of ocean color variables, such as chlorophyll concentration, remote sensing reflectances, turbidity, and we will have a focus on those products that are available for the North Atlantic region, for the North Atlantic Ocean. First, a few notes about the working environment. We are going to use this Jupyter Notebook platform, which is an open source web application that allows us to create and share documents. And these documents can contain all kinds of data. So you can have equations, text, code, images. But the most important bit is the code that you can run basically in real time, as you will see in a moment. The platform supports a variety of programming languages, but today we're going to be working in Python, which is one of the most popular, widely used modern scripting languages. So you will have two types of cells when you go through your Jupyter Notebook, text and code. Basically, you can make the two of them apart, because as you can see in here, the code boxes are numbered. So to execute each cell, to go through the code, you basically have to press the play button up here in the top panel. You can use the stop button, which interrupts the execution of whatever box you're running at that time. You can copy cells, you can add new cells, cut one, and you can do whatever modifications you want to this Jupyter Notebook, and you can save the notebook, and you can even use this file new option in here to select a notebook and create your own from scratch. So the objective of this training is to understand how to use ocean color to study different ocean processes. So in general, we can talk about two components. In the global model of the ocean, we can use ocean color data. The first one is the biological component. So we can detect chlorophyll from space using ocean color sensors, and then use this chlorophyll concentration data as a proxy for phytoplankton. As you know, phytoplankton is the base of the marine food web. So the dynamics of phytoplankton at seasonal and interannual scales can give us a lot of information about the marine ecosystem, but also about things like the global carbon cycle. We can also use chlorophyll concentration to derive some other variables, such as the primary production, which is listed in here, which gives you an idea of the amount of chemical energy which is released into the marine environment through photosynthesis. And we can also calculate the specific concentrations, chlorophyll concentrations, for the different phytoplankton size classes, which will provide us information about the community dynamics, or the community composition of the phytoplankton. And then we have a second component, which is formed by the geochemical variables of the ocean. So we usually catalog those as optical products, as you can see in there in the text over there, and that's how you're going to be able to find them in the Copernicus Marine Catalog. And in here we have variables such as turbidity, absorption, scattering coefficients, transparency, that provide information on the other water components that can be present in the ocean apart from chlorophyll, such as suspended sediments. And this will help us study some other processes such as erosion and even pollution. So the important thing, the takeaway message is for both of these categories we use the same underlying ocean color technique. So this technique measures the solar radiation that is backscattered out of the ocean after interaction with water and its constituents. And we have discussed this briefly during the presentation. And this detection is a spectral result. So basically we can tell not only the total amount of radiation, we can also tell from the product the amount of data of radiation detected in each one of the wavelengths. And then we can infer which one of the water constituents is responsible for the backscatter at that wavelength. So let's see a pretty picture, which is always a good way to start a workshop. Here we have a fantastic example of what ocean color is capable of detecting in this image acquired on the 20th of March 2003 by SeaWips, which is one of many ocean color sensors. This one in particular is part of one of the NASA missions. And in here, you can see that light is not only being reflected by water, but it's also being reflected by clouds and dust that's present in the atmosphere. So we have 3 exercises prepared for you. 3 parts important. Part 1 and 2 will focus on the biological component, and part 3 will focus on the optical component. And we will use this first notebook to familiarize ourselves with ocean color data, looking at the data structure, learning how to open files, to extract data, to plot it. And then in part 2 and 3, we will use the data to study some more interesting events that have an ocean color signature, such as, we have a list over here, a phytoplankton bloom detected off the west coast of Africa in 2013. We will put together a time series of chlorophyll for a region around the Canary Islands for different time periods of 2017, and we will get an idea of the general dynamics of the phytoplankton seasonal cycle. And we will also study the optical signature of the subaquatic volcanic eruption that occurred at the end of 2011 and beginning of 2012, close to the island of El Hierro in the Canary Islands, that had a really strong physical and optical signature that we will see in part 3. So we can scroll down a little bit to see the data, or the data sets, to define the data sets we're going to use. So all the data we're going to use for this exercise is the Atlantic reprocessed chlorophyll data sets at level 3 and 4. So you can see here level 3 and 4. And then the global optical reprocessed data set at level 3. For all of them, we will use the reprocessed version of the data as opposed as the near real time of the data. And reprocessed data is usually labeled as REP. So what does it mean? So using the reprocessing data means that the data has been processed using the best possible available ancillary data. And also this means that data streams for all the ocean color sensors that are available have been aggregated together to provide maximum coverage. So in the context of Copernicus Marine Service, level 3 data are products that provide a daily snapshot of a region, in this case the North Atlantic. And for level 4, we can aggregate data for a longer period, like a week or a month. And for some of the products, we also can fill the gaps left by clouds by using some interpolation techniques. It's important to have in mind that the ocean color data we're going to use is exclusively obtained by satellite observations. We have not integration of model data of in situ data. And to do this, we need to develop regional algorithms. We kind of discussed this during the presentation, because we need to take into account the special bio-optical properties of the water masses we are studying. So we develop algorithms that have been optimized for those waters. You can learn a little bit about the products if you click on the links that I have provided in there. Those links will get you to the Copernicus Marine Service catalog, and particularly to the product manual document and the quality documents. And here I've just provided a snapshot of the level 4 Atlantic chlorophyll product for reference, so you can see here the extent, the geographical extent of the area, and some basic information. So right, we have a kind of a motivation. We set up the objectives. So let's get programming. The first block of code we have in here is gonna we'll set up our environment. So in the context of computer systems, an environment is a namespace where keywords are assigned to functions, and then those functions are get called when the keywords are used. For example, in here we use PLT as the keyword for the matplotlib pyplot library. So what's a library, you might ask? So in programming language, all the functions needed to perform a certain type of task are usually bundled together in modules or libraries, and we are going to be doing in here in this first box of code is to import the libraries, making them available to use through the whole exercise. So typically, as I said, a library will contain all the functions needed to perform a task, and Python has a great variety of pre-existing libraries. For example, we were going to be using the following list. So we will be using Xarray for data loading, then we have the matplotlib, which aggregates tasks that have to do with data plotting. We use Cartopy to produce great maps of the oceans. NumPy, which is probably one of the most known libraries, is usually in general for array manipulation. So that's everything from logical operations, aggregating data, selecting data that fulfills a certain condition. Then we have the datetime library, which defines time and variable, date and time variable operations. We have the OS library for those functions that are dependent of the operating system. And finally, we have the string library for string manipulation. So once our environment is set, we can start looking at some of the data. First, we will do the basics. So that's defining the names of the files we're going to use and where we can find them. And to do this, we will create a variable called root there. This variable over here. And we will assign it to the current working directory. So that's exactly what CW means in here, current working directory. Files will normally be archived in a directory, in some directory in your computer. So, but for this workshop, you can assume that all the data is available, is in the same folder inside a subfolder called data. So you can put the data anywhere you like, but you will need to change the paths that we have defined in here if you're using data from outside the data sets provided in the workshop. So this also gives you a good example of how the modules in Python are organized. So you have, for example, the OS module, and you access the get working directory, current working directory function by using a dot in here, and you can nest this module access. So for example, you can access the join method within the path sublibrary within the OS module using subsequent dots, basically. So what we are doing here is to using the join method to build a path to a data directory using two strings. One of them is the one that we defined using the root directory, get working directory, and assigned to the root directory variable, and the other one is the string date. And you can see what those two variables look like after we do this assignment by using the print function. So basically, you passed a variable in between parentheses in here, and then that variable gets printed on the screen over here. So you might also note some difference between my output and your output, and those will probably be due to differences in operating systems. So for example, I'm running in Windows at the moment, so we use the slash to travel through different directories and subdirectories. But if you're running in Unix, you will be using a backslash to define the same structure. So as you know, the data is in netcdf format, which is denoted by the NC extension. netcdf is a self-describing machine-independent data format, which was especially created for sharing scientific data, and that's exactly the data format we use to distribute the products in the Copernicus Marine Service. So with this coding here, we have defined where our files are, where the file names are. Will be defined in the next box. The files are named using the Siemens naming convention, and you can find more information about this naming convention in here, but it's quite straightforward. You usually have a string that identifies the date. You have different identifiers. So M stands for monthly and D stands for daily. In the case of monthly, you will have another date, so that's the start date and the end date for the product. The OC stands for ocean color. PML stands for Plymouth Marine Laboratory, which is the production unit in charge of producing these data sets. Then we have an identifier that describes the level. The general product name, chlorophyll in this case, the name of the algorithm, so this is where the regional algorithms come in play. So for the North Atlantic and also for the Arctic Ocean, we have a regional algorithm called OSIFI-CI. Then this identifier over here tells you that you will be using data that uses different data streams for different sensors, different satellites to build a final value. This over here gives you information about the resolution. So these two data sets are 1 kilometer. This is the describer of the area. So ATL stands for North Atlantic. And this tells you that the data is reprocessed, which we have discussed in the past. So we have defined our our file names in here, and we have defined where these files are going to be, and then we can start ingesting data. So this is the final path, for example, for the CCI chlorophyll level 4 monthly dataset. So we can start loading files and accessing the data inside them. So for all this, we will use the Xarray module that we imported at the beginning, and we will load the file to create a new dataset using this open dataset function within Xarray. So in here we have the simplest version of open dataset, which takes one argument, and that argument is the path for your file. So this is exactly the same thing we had printed in here, but it has lots of options. And one thing that you need to take into account when using open datasets, the open dataset function, is that the file opens in read-only access. So that means the open dataset creates a memory copy of the dataset you are opening, and if you modify the dataset, only that copy in the system memory is modified. The original file remains unchanged. So in the next box, we will explore a little bit more what's inside the level 4 monthly file, and to do this, we just use a print command in one of the datasets objects we have just defined. As you can see, the data is organized in 4 categories, so dimensions, coordinates, data variables, and attributes. So the dimensions represent the physical dimensions of the data, so that's things like latitude, longitude, time. data variables. So each one of them represents a set of values that have the same type, and in general they have a biogeochemical significance. So for example, obviously this one is the chlorophyll concentration. Then you have coordinates, which are just above, which are special variables that have a correspondence with the dimensions. And finally, you have attributes. These attributes provide useful information such as the data source, version numbers, resolution, the CMEMS production unit, links to documentation, so on. So we can actually see each of these accessing the different fields within the dataset object. So we have 4 fields, one for dimensions, data variables, coordinates, and attributes, and that's how we access, for example, the dimension fields within the CCI chlorophyll level 4 monthly dataset that we defined in the above. We pretty much get the same level of detail. For the dimensions, so we can see the length of the latitude and longitude. This gives an idea of how the data is sampled, or in other words, if we think about an image, these are a measure of the height and width in pixels. And then we can print also the coordinates, which gives you a good preview of the actual values inside the arrays. So you can see our products are created equidistantly in latitude and longitude. So the distance between pixels, if you look at it in degrees, is a constant. This might not always be the case for the products, so don't take it as granted. And then we will have our variables, which are organized in a dictionary. Dictionary is a data structure that defines a list of pairs in no particular order, and each one of those pairs has a key and a value. And as you can see here, let's see, dictionaries in Python are defined in between curly brackets, and then you have a list of the key value pairs. So for example, in here, latitude is the key of the first pair, and all this is the value of the latitude element of the variable dictionary. Same thing for the longitude. We have grid mapping, chlorophyll count, and what else? Time bounds, should be a chlorophyll error somewhere. So while the values of the data can take any value, basically the keys have they all need to be unique, and they all need to be in the same data format. And then finally we have the attributes that you can access using the ATTRS field. And these provide a ton of information, as you can see. Let's see some of the interesting things. So we will have some things like the file quality index. We have 3 levels of quality, so 0 is the highest. The product level, the identifier of the area, which we already discussed on the naming convention. This one is important, as it gives you information of how to credit Copernicus Marine Service when you're using your data in a paper or in an analysis. What's the parameters, start time, and all types of information about the software, which might be a little bit meaningless if you're not involved in the data production, but it's actually quite useful if you need to keep track of changes in the software. Grid resolution, so we already discussed that this data is 1 kilometer. This is another important one, and it's actually a really long one that goes up to here, basically. So this gives you the history of the file. So this is a monthly file that we have built aggregating data observations from each day during this month. So this is June 2017. So this will actually identify all the different daily files, and then it will tell you what we've done with the file. So we did a mean temporal composite of all these files, and then we added the standard deviation error account variables. So, and finally, so just to mention it, there's the CF conventions. CF is short for climate and forecast. So this is a metadata convention that defines the minimum standards for data to be used in climate studies. So we have seen how the files are organized internally, and we have learned the meaning of some of the different parts, which are roughly the same for all the ocean color products. So what we've seen in here can be extrapolated to the datasets we will use in parts 2 and 3, and even to other physical variables. So let's now look at the individual variables. Let's extract some of the variables from the monthly file that we've been using for our exploration. So in this particular code box, what we're doing is to extract the different variables from the monthly dataset, and we are assigning each one of the variables to a named Python variable, which will save us time and space when we use them further down in the code below. You can also see the difference between accessing variables, which are fields within this dataset object, and you can see the difference between accessing that and accessing things as the latitude on the chlorophyll, which are elements of variables, which, as we discussed, is a dictionary. So this is how you access a field within a dataset, and that's how you access the value of a certain keyword or key within a dictionary. So by printing the content of these variables, we have pretty much the same information as above, but in a better format, basically. And we are no longer printing also the whole dictionary of all the variables, which can be quite confusing. For example, in here we've run the print command over the monthly chlorophyll variable, and the first line of the metadata tells us that the chlorophyll value is a 3-dimensional variable, has 3 dimensions, time, latitude, and longitude. And when we extract we will extract the data further down, we will use these 3 dimensions. We will access these 3 dimensions using 3 indices that will represent the time, the latitude, and longitude dimensions, respectively. We have some metadata that describes the chlorophyll as the mass concentration in seawater and units of milligrams per cubic meter. We have values, an idea of what the valid minimum and maximum values are for this chlorophyll algorithm, and the cell methods, and basically it tells us an attribute that tells us that each value of our monthly composite is the mean, basically. It's the mean of the daily values of during that month. In the same way, we can try to print the monthly latitude and longitude variables. As we saw above, in the length of the latitude and longitude, the fact that we only have one number in here means that both latitude and longitude are 1-dimensional variables. And these numbers, these 2 numbers, define the shape of the multi-dimensional variables that use latitude and longitude as dimensions. So for example, if we go back to our chlorophyll, the width of the data is 5,664, which matches the length of the longitude in here. Where is it? Longitude in here, and the same for the latitude. So we have the height of the data that matches the length of the latitude, and then the depth, so to speak, is 1, which matches the length of the time coordinate. Don't let yourself be confused by this valid maximum and minimum values that we get for the latitude and longitude, because these tell you what the valid possible values are as opposed to the actual values. We will have to look at the data rate to see the inside the variable to get the geographical extent of the latitude and longitude variables. In our case, this is the Atlantic region is defined from 46 degrees west to 13 degrees east in longitude, and then it's described from 20 degrees north to 66 degrees north in latitude. Bear in mind that these coordinates over here describe the coordinates for the center of each one of the pixels, but they don't match exactly the numbers I've just told you. And last but not least, we can print our monthly time variable, which is a one-dimensional array, which a single time interval element, this one in here, that describes the period of time covered by the monthly composite. So that's for the first day of the month until the last day of the month. You might remember that at the same time we define our monthly data set, we define also a data set called CCI chlorophyll level 3 daily, using the daily file name as an input. So we can use the same command to investigate the daily variables, printing the chlorophyll over here, the latitude and the longitude, and this is in the time as well. So this is a small exercise for you. I suggest you take a little break here, you pause this video and compare the output of these different print commands between the monthly composite and the daily composite and try to detect the differences. So now you've done that, hopefully. We can continue to the final section of this first exercise and learn how to visualize the chlorophyll data that we have loaded and extracted in the steps above. So the most straightforward way to visualize data array is to use the image show function, which is distributed inside the matplotlib the pyplot library we imported at the beginning. And this, as you can see, returns a matplotlib image access image object. As we discovered during our data exploration a minute ago, chlorophyll data is described by a three-dimensional array with the 3 dimensions represented the time, the latitude and the longitude in that order. So when variables are stored in an array, individual values can be selected using indexing, and we will need 1 index per dimension. So that's 3 indexes for a 3D variable as the chlorophyll. Why am I telling you this at this stage? Well, to use the image show function with our data, we need to reduce our 3D chlorophyll array to a 2D array. So this function in here only likes 2-dimensional arrays. And this is done easily, and we do it here by basically ignoring the time dimension, which doesn't give as much information anyway, because the daily privilege is just a snapshot of the status of the ocean in one day. So the time variables is just the timestamp for that day. So basically we are making use of those 3 indexes, and in here we are selecting the first and only item along the time dimension by specifying its index. So this is something that you might not know, so you have to bear in mind that Python uses serial indexing. So that means that the index numbers start at 0, not at 1. So this operation here is called slicing, and by selecting this, we are just slicing the 2 last dimensions and making the 3-dimensional array into a 2-dimensional array. So we will come back to this slicing technique later, which is not straightforward. But if you have some curiosity now, you can always print this sliced array part and see the shape, and you can compare the shape with the non-sliced daily chlorophyll variable dataset. So let's go back to our map for a second. So this might be the quickest way to visualize the data, but it's certainly not the most informative way to visualize the data. To start with, all the data is plotted in the same color, solid block of purple. It's tricky to make apart the land from the cloud, even if you're familiar with the geography of the area. And even worse, the X and Y axes are formatted using the indexes of the array instead of the latitude and longitude, as is usually the case when we have maps. Thankfully, we have the Pipeline library, which can be used together with the Cartopy map creation tools. We have imported all those libraries above in a more or less effortless way to create a much nicer visualization of the data. So first, in here, we will learn how to create an empty map, and then we will learn how to populate it with chlorophyll data. We use PLT figure to initialize a new plot object. So this basically creates a new figure object, but that's empty so far. We use PLT access to that access to the current figure and make them the current access. And the most important bit about calling this function is that we need to define the projection. So again, we need to stop here to explain the concept of projection maybe. Map projection is a way to transform the globe, so the surface of the Earth's sphere, and we want to convert that or process that into a plane. So basically we want to go from sphere to a map, which is flat. To do this, we need a systemic way to transform the latitudes and longitudes of the locations on the surface to actual locations in the flat map. And there are infinite ways to do this, and the good or the bad news is none of them is totally correct, but some of them are more useful than others for different applications. So in this particular case, we've used this projection in here, which as you can see, for example, is great to visualize the African continent, but it kind of flattens the data around the poles, so it will be no good to visualize data, for example, around Iceland. So once we have this defined the axis of the figures, so we define it in here and we assign them to an AX, a variable called AX, we can define things as the coastlines using the coastal methods of the axis, the actions object, sorry. And in this way we can add all kinds of formatting, as we will see in a minute. In the same way, we can try different projections. So in here I've used the mobile projection that models the Earth as a perfect 2-to-1 ellipse. And then there's this azimuthal equidistant projection, which is a polar projection showing the meridians as straight lines. And the good thing about this projection is that it's great to visualize data on the poles, and the distances for the points to the pole are actually correct if you use this information. I think I have provided a link to a list of projections that are available in the Cartopy module. Sorry, I didn't want to do that. So as a suggestion, you can try to set up your own custom map in here for the North Atlantic with checking on that link the different projections, selecting one that you think is going to be useful to visualize the region of interest, and then using the same tools, so basically this type of code sequence to create an empty map with coastlines. And now we have seen different projections. Now we know to set up a map, an empty map. We can populate it with chlorophyll data. So the following code box is way longer than anything that we've seen so far, but it's very straightforward and very intuitive. So please do not panic. So the first thing, this first 4 lines you know already. So we will define a projection. So this is the first one we saw, and we will call it my projection. I initialize a figure object. So it's this instruction in here, and we can specify the size of the figure and the resolution of the figure. We will then create access to the existing plot, the existing empty plot, and make those the current access. So we will basically pass the projection that we created in the first line as the argument to the plot access function, and we save the result on the AX variable as we did above. And last but not least, we add some coastlines that we see above. So far this is what we know. Now we will do the actual plotting. So let me skip this bit of code for the time being and go straight to this one. So to do the actual plotting, we will use the pcolorMes function to create a pseudo color map. So in this pseudo color map, each data point is drawn as a cell, as a big cell region on the plot, and that chunk of area basically is colored depending on the value of the pixel is representing. So the plot colorMes function needs 3 arrays as an input, and the first 2 have to be 2-dimensional arrays defining rectangular grids, and this means that before we can call pseudo colorMes, we need to convert our latitude and longitude, which you will remember were 1-dimensional variables, into a 2-dimensional coordinate mesh. And we do this using the numpy mesgrid function, which is the line that I had skipped so far. Once we have that, we can understand where those 2 variables come from. And this is a representation of the chlorophyll. We will talk about that in a second. We have only a few other arguments. So we have CMAP, which is a color map instance or a registered color map name. So the color map is the bit that maps the data values to the colors that we are going to use in the figures, and we will see different color maps further down. And we can also define variable maximums and variable minimums that will specify the range that we are going to use in the color map. So if these arguments are not mandatory, so you can just skip them, but if you don't use that, the variable minimum and maximum will be extracted from the variable you're plotting. So this is the daily chlorophyll variable for this case, which is not always ideal, for as you will see in a second. So let's go back to this bit over here. So bear in mind we have chosen to plot the daily chlorophyll variable in logarithmic space. There are 2 reasons for this. First, the chlorophyll values, as we saw, we will see in a second when we will plot our first map, take values across 2, even 3 different order of magnitudes. So using a linear scale makes things very difficult to interpret. And secondly, if you look at the chlorophyll global across the ocean, the global chlorophyll is known to be log normal. So in other words, if you calculate the logarithmic values of the chlorophyll at global level and you plot them, those values form a normal distribution naturally, centered around 1 milligram per cubic meter. So this is a very specific case. So the chlorophyll is a very specific case. So logarithmic scale might not be useful for other variables, such as the optical variables we will see in part 3, which are better visualized in linear space. And basically, with this instruction over here, we're mostly done. Believe it or not, the rest of the code is just formatting. So we use AX grid lines to define the grid lines and to tell our plotter that the grid lines will be labeled. So that's that option over here. Labels will be drawn on the 4 sides of the figure by default, but we can override this behavior. In particular, the next 2 lines over here make the top and the right hand labels of the figure just disappear. The next 2 lines define the next 2 lines define the things as the size and the color, and you can even select the font of the grid labels. Then we have these two functions in here, which are methods from the axis object that we did defining above. So that's setting the x limit and y limit. And these are useful if you want to define the geographical extent for your map. Basically, what you're doing is specifying minimum and maximum values for the x and y axis. We can add a color bar in here. So that's the color bar method in the PyPlot module. This color bar will show the correspondence between the colors and the values and will facilitate interpretation of the data. This has several attributes, so basically you can define if the orientation is going to be vertical or horizontal. You can define the size and the location of the color bar respective to the figure. We can define the ticks that are going to appear in the color bar, and in the next line we will define the labels for those ticks first. So you can define ticks that have no label and labels that have no ticks, for example. And then we have this line over here, which uses a set label function over the color bar object to set up a big label that will go to a color bar. Then we have the title function. You basically pass it a string and some formatting information, and it will give you a big title for the whole figure. And last but not least, we will use PLT show, which will result in this marvelous data set and this marvelous map of the chlorophyll data set. So basically you have here your color bar. You can see that the scale is logarithmic. These are the text and the labels we defined. Some comments on the structure of the data. So you can see here sharp straight lines. Those usually are due to two different streams of data. So that one satellite goes this way and the other one goes this way, and then you overlap the passes and you composite them in one image, and you have a triangular gap in between the passes. The rest of the white areas are more organical, more weird shaped, are mostly due to cloud cover. They can also be due to data that is masked because the algorithm chlorophyll has failed or the atmospheric correction has failed. So that's it. That's the basic first map of daily chlorophyll concentration using ocean color observations from satellite. So small exercise for you. You can have a play with the different formatting. You can probably easily Google way more options and many ways of making this plot even more exciting. But we will try to save some time and go straight to the plotting of a monthly data set. So we can now visualize the monthly data set in exactly the same way. I won't go into much detail because the code is exactly the same, but again, I can suggest that you can try to change the color of the continental filling, so that this here over here, so we can tell where the land is and where the cloud is. We see them at different colors. You can try to label the latitude and longitude axis. We haven't. You can play with the axis limits, so those set x limit and set y limit functions that we saw above, that we will give you different maps as well. But the important thing here is that you can compare this daily map, which we obtained for the 15th of June 2017, which has pretty normal coverage, maybe not very impressive coverage for summer. For some reason, it was clearly a cloudy day. We can compare that with the monthly composite for the same year, the same month. So by comparing the two plots, you can see the impact of data aggregation. So to produce the monthly files, we have, as we said, composited a whole month worth of daily observations and calculated the monthly average for each one of those pixels. And it's very clear how this type of temporal aggregation increases the coverage. So you have way less masked pixels in here. But it also has a smoothing effect, which might lead to some information lost. In particular, we might be missing some of the short terms or punctual point events that are visible in the daily composites in here. In particular, for this area, even if the coverage is not really good, we can see that going from the daily to the monthly composite means that we lose a lot of definition on the edges of these structures over here, and also the intensity of the bloom that you can see of the coast of Ireland has decreased a lot after doing the temporal aggregation. So to finish this section, let's see that slicing technique that I mentioned above in a little bit more detail. So we will do that in the next 2-3 boxes. So we will use slicing to zoom in into a geographic box around the Canary Islands using the monthly composite as an input. So we will first define a coordinate box around the Canary Islands. So that's exactly what we do here, just straightforward variable assignation to numbers. Then we will use this function in here, which is distributed with NumPy, with the NumPy module. So the where function helps us identify which array indexes are inside that coordinates box we have just defined and which ones are outside. So these two calls over here will compare the monthly latitude with a minimum and a maximum that we have just defined, and the same for the longitude, and it will return a two-dimensional array telling you where the latitude is between these two inside this range, and where the longitude is inside this range. But if you remember, our original latitude and longitude variables were one-dimensional, so we need to convert them back to one-dimensional variables, and we use the NumPy squeeze function, which is over here, to do this. Let's convert the indexes arrays back to vectors, basically. And finally, we can start zoom in data for the chlorophyll latitude and longitude. And this is done by, if you remember, the first time we talked about slices, we had two columns in here. So we replaced those columns with the subset of indexes that we have obtained by imposing these two logical conditions. Then we are able to extract the chlorophyll latitude and longitude inside the box. So if you're interested, I have explained the inner workings of slicing in terms of start and end indexes a little bit more in detail in here, but it's not essential for the exercise, so I'm gonna go straight to the end. The important thing here is that we have defined zoomed in data rates, and we can now create a chlorophyll map in the same way we did for the full region. So at this point you will know a lot about plotting, so you can try to implement any formatting changes you may want in this particular code. As you can see, the resultant data set, the resultant map is pretty similar to the one that we saw above. For the, where is it? Here, over here, for the whole Atlantic region, but we are basically zooming in this data, in this data box. And I've also used a different color map. This one is called magma, as opposed to the one above, which is called verdes. So you've made it through here. Well done. I hope you have enjoyed this practical session. It's a lot of information, I know, so take your time. You have done a great job. So feel free to stay here for a little bit longer, play around with the data, all the possible ways to visualize it. I've left you a little bit of a challenge in here in case you're up for it. So you can try to use exactly the same tools we've used in here to extract primary production data So basically I've kind of hidden a primary production file in the data folder that you have in here. And then you can load and extract information and see how the global and the regional data differ, and how the primary production data differs from the chlorophyll data, and choose the best way to visualize primary production. If you want something that's shorter, you can also explore some of the other variables that are distributed in the chlorophyll product. So those were the chlorophyll counts and the chlorophyll error. And when you're ready to move on, I will see you in part 2.